So, the talk is not a super strict roadmap, so don't believe anything I say, basically. It is, however, a rough idea and explanation how all the things fit together. So we will actually start in the past before we go to, okay, what the future holds. So just wanted to underline, not strict outline for future development. So, my name is Konrad Malawski, Ktoso, also online under that nickname. I do a bunch of community stuff in Poland, but actually moved to Tokyo now. Enough about me. Akka obviously used in many places, and here's the question to you guys and people. Who's using Akka? Jesus, everyone. So you came here to see what's next up, right? I hope this is gonna be the right talk for you. This also means that I'm gonna skip over some of like basics. If almost everyone raised their hand that they actually use Akka, let's just skip over it. So the underlying motto of, it's not like an official motto of the team or anything, but really it's something I at least have in the back of my head when we design new stuff. It's, okay, there's some status quo and how can we do better than that, whatever the status quo already is. And another one that's very recently popping a lot into my mind, at least, when we see like other tools or frameworks or libraries do some stuff, it's, yeah, we've been there, we've done that, it doesn't work. So there's a lot of things that we learned the hard way, but also a lot of things that we probably will learn the hard way in the future. So it's a talk about a mini journey, like where Akka came from and where it's heading. And like I said, the past, let's cover kind of quickly, because we want to focus on the new stuff. But it's important for context. So we start out at the mountain of Akka. As you know, first release around 2009 was mostly Jonas working on it back then, was his Akka actor kernel back then. And you can see all the buzzwords in the like subtitle, like RESTful distributed, persistent transactional actors, all of the buzzwords, right? Obviously, to get some attraction, gotta have those. But the core of Akka was always and still is the actor model and actors. Who of here present people was in Roland's talk just before this one? Some of you. Okay, so I'm not gonna have much overlap, because this is more like we will mention typed, but it's not like we will learn typed in this talk. So the core of actors is always free operation. They can send messages, they can change their state. So in Akka Typed, that's basically becoming a new behavior. So very nicely modeled there. I think in Akka Typed, we're actually much closer to the original definition than we are in untyped actors, because in untyped actors, becoming is like an extra feature, right? You have this method on context, and you can sometimes maybe do it. In typed, it's really a native feeling thing that you all the time become a new behavior. So we're a bit closer to the origin in the new APIs, actually. And obviously, you can create other actors. So a concurrency and a distribution construct, but most importantly, it's a distribution abstraction, right? It models distribution. Sometimes people use actors only for the concurrency aspect of it. That's perfectly fine, but it's important to remember that they do a bit more than that, right? If you use actors, you can go distributed with them very easily, and it feels right. Whereas if you try to use some RPC systems, they go the other way, right? They try to make the distributed thing look like a local thing, and that doesn't always match, right? Because the network, then the call in has latency, it can fail in different ways. What we have is, we always have messaging, and making that distributed feels more correct in that sense. And the only failure mode in actors is really not getting a message in that sense. Okay, actors, if anyone has not ever seen an actor, here's an actor. If anyone has not seen the new Java DSL, anyone cares about the Java DSL in this audience? Some people. I would like to actually underline that we do spend a lot of time on it. Sometimes people think that, yeah, it's just they did it in one day and they don't care about it. We spent a lot of time on making all of the APIs make a Java DSL. All of the contributions also have to have a Java DSL, which Heiko here is not happy about. But everything in Akka has a properly nice feeling Java DSL. So totally first-class citizen in that sense. So okay, obviously you can do like a request reply thing, but that's not the interesting thing. Yeah, that's just when I was doing the slides, Intel announced the many cores processor, so I was really excited. But the more exciting thing is that we are not bound to all the time doing request reply. We can do like request and please tell the other guy about something, right? So we have more interesting communication patterns than just request reply all the time. And another thing that I did want to put it in the talk because people sometimes forget is that one of the reasons and also differences between what I call the outside world and the inside world is if you control your environment, as you in an Akka cluster do, you can do some kind of different trade-offs. And such a trade-off is, for example, when you have a web API, it's usually going to be HTTP with JSON or XML, right? If you internally use actor messaging, you're in a more confined and controlled environment, and you don't have to do the JSON over HTTP. Why do I talk about that? Because performance-wise, these are, I think, nanoseconds. Yeah, nanoseconds. That's how fast you can serialize a message using protostuf or protobuf. Okay, just get a rough idea. You don't. All of these slides, we have a lot of them. Don't attempt to read all of it, but rough idea. Okay, a few thousand or 100 nanoseconds. Then a few other serialization engines, yeah, comparable, a bit bigger in size, but still comparable. And this is the default what people use, right? JSON, that's the serialization times, that's the size, and that's the Java serialization, which is the default one. So you'll notice, and that's again something in the future, that we have started issuing warnings if you use Java serialization. So that's like a current thing. And in the future, we'd really like to move towards actually not having it, because what people do is they see, okay, it works, because by default Java serialization is on, you can pass your messages onto the network, and it works, and then it goes to production, and then at some point there is a complaint, oh my god, but it's slow. I wonder why. I don't mean to be not nice, it's just, the truth. So here's how a serialized Akka message could look like. An order message, Java serialized. Dashes are just some binary that's not printable. So even XML is smaller than that. Think about that. XML is smaller than Java serialization. Obviously, because XML doesn't carry the typing information, etc. But yeah, that's one of the reasons the Java one is slow. JSON a bit smaller, doesn't really matter that much. With binary formats, you can get way smaller. An interesting thing to remember, some formats actually do carry along the actual type information, like Cryo does here, and some formats completely don't. Like protobuf doesn't carry any type information, it just carries along a number. This field is this numbered field in the message. So, we internally use protocol buffers, and that's again, in the future we'd like to enable this by default, that we would like to not allow Java serialization. Currently, most of Akka doesn't use Java serialization. Sadly, we had a few things that still do, mostly remote deployment, which we would like to remove anyway. So if you, for example, in your system, you're using Cryo or something, then you can enable this flag, which will make the Akka things that still use Java serialization for compatibility reasons with old versions. If you set this flag, we switch to everything to protocol buffers. So also good for security, right? There's a lot of attacks on Java serialization, so also a security thing. How much configuration is that? Just that, so not much. As I said, slides are not for reading, because we have a lot of them. Like literally a lot. So, side note, binary compatibility. Anyone not know about the new binary compatibility rules we have in Akka? It's relatively new, right? So, quick explanation. It used to be that 2.2 to 2.3 would be breaking changes, right? That's kind of what Scala does, right? The 2 is like forever, it's epoch, and then major. So since 2.3, we actually do the normal major, minor patch versioning, right? So that means that 2.3 was actually binary compatible with a 2.4 line and all of the patch versions, and all of the 2.4 releases are actually compatible with a 2.5 release. So for example, if you're using Akka HTTP right now, it still depends on 2.4, and that's because we don't want to use features from 2.5 accidentally. But you can just set the version to 2.5 and it will just work, right? So some things to remember about the version compatibility there. And eventually there will be a 3.0, but so far we don't really see a reason to call one. It would be like big changes when, for example, we make everything Akka typed and untyped is not a thing anymore, like a really big thing. But for that to happen, you know, many years, and everybody would have to have adopted Akka typed, for example. So far no plans for Akka 3 because we can just continue with actual compatible timeline. And it's not it's not wire compatibility, and we'll get to that soon. So, quick sidestep. So, for those of you who remember, there was a time where everyone had their own future implementation, including Akka, of course. And the most notable ones were, I guess, in Lift, Scala Z, and Finagle, and Akka. And there was a SIP, and now Scala has the futures we know and love. And I'm only calling this out to talk about the next point. So, okay, we have futures, and what people do with futures is, for example, they have a loop, like from 0 to 1,000, and they want to do some operation 1,000 times. So they would do that in blocking codes by just doing the blocking code inside of a loop. And then you give them futures, and they just call it 1,000 times at the same time, because the future is asynchronous, does the processing in the back. And a thing like that could happen. So you're just firing requests to some service, and the service, as here drawn, is overwhelmed by all the requests you sent to it, because you didn't really wait for the actual response to get back, you just fired 1,000 requests. And then maybe it gets back with a response, but actually it starts blowing up, right? So we know that, we can solve that in many ways, but people nowadays, and back then already, solve it by circuit breakers, right? Akka has had circuit breakers basically for futures and all of the APIs interacting with futures, and now adapted by Hystrix and many other APIs. Not really a new thing. But what does it really do? So we back off for a few seconds and then we try again, right? So I call it the slamming the brakes pattern, where you have a car and you actually didn't slam the brakes, but you actually crash the car. This is the circuit breaker triggering, right? And it says, okay, we gotta wait 5 seconds. Okay, now it works. And then you're like, boom, again, right? And then you're like, okay, now it works again. That's basically circuit breakers. Circuit breakers get to the point of the thing failing, and then they back off. Okay, remember that. And can we do better than that? Right? That's way back then, because you're kind of guessing, okay, how much can this service or this API handle until it blows up? It's not flow control. It's like failure compartmentalization. And we can do better. The answer is basically reactive streams, but it took us a few years to actually realize that. For a while, everybody was kind of content with circuit breakers. So the next stop in this trip is the cluster oasis, in which we discover the wonderful world of distributed computing. So far, we were only multi-threaded, basically. So what is the cluster really? And even the first sentence on this slide is actually something not many people realize. The Akka cluster is strictly about membership and failure handling. But it's a membership thing, right? It's you have a bunch of nodes and you want them to form a group. That's what it does. It's not, sometimes people compare it with some, I don't know, like a clustered database. That's not the Akka cluster. We'll get to actually storing data. Okay, so it's only a building block that actually puts nodes together and they monitor each other and then they can decide, oh, this one is down or not. Okay. On top of that, cluster tools like cluster sharding and cluster singleton, etc., are the actual thing that helps you to build distributed systems by making it a bit simpler. Again, the entire idea is in Akka is to make things a bit simpler, but not too simple so you don't have control over stuff. So with sharding, anyone not used sharding? Okay, so quick overview. Sharding basically works like that. You get a message, here K5, it extracts where this message should be routed to, like with database sharding, for example, and it routes, okay, so K5 messages should go to this actor 5. Because, for example, we route by whatever message has the 5 in it, we go to the actor 5. It can be anything. And then you'll notice if a node fails, cluster sharding internally notices that, and it can migrate these actors, like this 40 actor, to a still alive node, right? So if there are messages that would have gone to this node that is dead, now they're going to the new node. And I say migrate the actor, right? But that's kind of fuzzy. We don't magically migrate the state or anything. And this will be the reason why we then go into Akka persistence. So what does it do? Heartbeats and failure monitoring, on top of which we then can provide features like, okay, failover and things like that. So this was all kind of the inside, so Akka talking to Akka basically, or to futures, which could be anything. So we kind of have to build a port to kind of welcome the traders from abroad, or to talk to them. So I call this kind of like interaction with the outside and inside. Sometimes people think about it data on the inside, on the outside from Pat Helland's paper. I think it's basically the same trade-off. Internally, you can do a bit different, a bit faster, a bit more efficient because you actually control your environment, and externally people want XML from you. So you're gonna give them XML. It's not what you would like to give them, for example, but that's what they want, or JSON. So we gotta have some HTTP interop. This was way back then known as Spray, which was super popular. I was a huge fan already back then. So Matthias and Johannes built Spray, and then we in the Akka team talked with them that, hey, maybe we can like join forces and make this a part of Akka. So this is how Akka HTTP came to be. The fully typed HTTP model isn't really new from Spray. This was kind of what Spray had from the beginning, but we did a full like revamp of the API, and I think it goes without, well, maybe it doesn't actually go without saying, but it's like a strong point that proves that it's a pretty good model if actual other libraries, instead of reinventing their own HTTP model, just use this one. Because we spent a lot of time making sure it's very correct and very thorough. So HTTP4S basically uses the Spray model, a bit adjusted, I guess. And again, a hint from the future, because in this talk I have a bunch of like these interconnected things, so it was hard to do the ordering right. So Akka HTTP is actually becoming the default backend for Play, right? There's going to be a slide about that, a section about that, but that also means, because we're actually parsing into the typed HTTP model, and Play always wanted to have a typed HTTP model, so we have that now, so the next logical step will be to actually expose the typed model in Play as well, to both kind of save on the parsing and converting between the two models, and also because a typed model is a really nice thing to have. And it's focused on and built on Akka Streams. So we're looping back to Akka Streams and Reactive Streams again. So we represent an HTTP server a bit, on one hand, similar to Finagle. So in Finagle, it's a function from request to response. In Akka, it's a flow from request to response. And a flow is basically a concept from Akka Streams. Who has seen Akka Streams in action? Many people have. So you know what a flow is. So a flow is interesting in an HTTP server because it exactly models what HTTP 2 can do. Right? Because in HTTP 1 you get a request, you do a response. You get a request, you do a response. What you can do in HTTP 2 is server push, which I don't like the name that it's push because it's actually still normal request response. But you can respond with more responses to a single request, right? Because you get a request for the main page of your website, and the server decides to already start pushing all of the images or all of the CSS files. And this is exactly what a flow can do. A function, well, it would have to maybe start sending a list of responses or something fuzzy. We have that here encapsulated in that flow type already. Entity, basically a source of byte strings. WebSocket is exactly the same like a request response, but the type is the same here, message in, message out. And the routing DSL is nothing new if you've seen Spray or well, Akka HTTP in the recent years. It basically says, okay, here's a path hello. If it's a GET request, complete with this response. And we have a low-level API, which is interesting for those who, A, don't like too many implicits. I think the only part of Akka that's like actually heavy on implicits is the routing DSL of Akka HTTP. The rest of it doesn't have almost any. And if you decide, yeah, I just want to get requests and do responses, you can use the low-level API. And that's also the integration layer with other frameworks like Play, right? So Play obviously doesn't go through the high-level DSL to then route again things because it already routed things because it has a routes file. Okay, so from the port of HTTP, we go to mount persistence, which is event sourcing for actors. Before, when we talked about the cluster, I said, and we magically migrate the actor. Obviously, there's nothing magic about it. And with just cluster and just sharding, saying migrate would probably be the wrong word. It's more like restart the same behavior in a different place, but it's not the same person anymore. What we can do with persistence is store, you get incoming commands, you persist events, and then if this given node dies, you move this actor to a different node and then recover the events, which effectively means it's kind of like the same actor, right? Because it behaves the same way because it's acting upon the history of all of its events. The feature here is that it keeps buffering incoming messages while it's recovering. So we handle, again, a bit of complexities for you here. API, if someone hasn't seen Akka persistence, very similar to Akka, just normal actors, but we did separate the two APIs. And that's something I want to explain why we did that, because sometimes people just assume, yeah, that's how it is. It's really important to separate the two cases, the yellow case of, okay, here's the incoming stuff, from, okay, this is the recovery. Because you most likely don't want to do side-effecting things while recovering, right? You don't want to redo all of the transactions you did to some bank account or something, right? And you may want to do that if you see that some of them are uncommitted, and then you do it after recovery. But having it really explicit that it's like in your face, think about recovery now, or think about actual life system now, we thought was very important. Previously, if anyone remembers the old APIs, well, this was experimental and we toyed around with it. We had a normal receive and there was a flag you could check if you're recovering or not. Which people didn't really think about that much. It would feel and write like a normal actor, so people would feel and write like a normal actor and then forget about recovery. So this is why we have like in your face two methods for it. So finally to the future. I did some like interconnections, like what's going to happen in the soon future, but let's look at relatively new stuff. So that's like current, but not future. But here I'd like to ask who has used the distributed data module, or the CRDTs? Way less people. And that's probably okay, because they have a very specific use case. So conflict-free data types, CRDTs for short, are kind of a complementary to Akka persistence. So we had Akka persistence, it tries to be consistent and partition tolerant. And then we were like, yeah, but we don't always really need to be that consistent. Like eventual consistency is a concept we like and have internally in the cluster actually. Basically the cluster membership is CRDT based without having been aware that it's CRDT based while it was being implemented, because that was before the CRDT paper, but the same concepts apply. And we wanted to provide this very useful abstraction to users. So it's available, so it can be a little bit out of date, but it will keep giving you answers. Whereas Akka persistence favors not giving you any answers if it suspects it could be wrong, right? That's kind of an intuitive explanation. So with CRDTs, what we do, and I'll jump right to the image, is you have some node, it does some local write, and this is a counter. So the counter works like that every node has its own slot, and the total count is the sum of these slots. This is how it's conflict-free, right? Because everyone just writes to their single slot in the counter. And then using the cluster gossip, this information is being spread in the cluster and deterministically merged until all of the nodes in the cluster have this information. This gossip is basically same like the cluster gossip, so it's a bit random. So the replicator sometimes decides, yeah, now I'll send data to node 1, and now I'll send data to node 2. And eventually all of the nodes have all the information, so it's eventually consistent. Another thing that you may have not noticed, and a person here in the audience has contributed a lot to, which is Jan, is delta CRDTs. Because here in CRDTs, we send the entire state all the time, and the state can get big because it gets bigger the more nodes you have in the cluster. Do you have a question? I'll repeat for the recording. Do we provide any guarantees for the convergence protocol of these CRDTs? No. It's like... okay, I'm curious, go on. You did the deltas, so... Well, yeah, I mean, obviously all of the CRDTs are convergent, but I think he's asking about timing or anything like that. Like, yeah, so timing is not deterministic. Yeah, and obviously all of them are convergent, both the deltas and the normal ones. That's kind of built in, and no timing guarantees. We do want to benchmark this in like a real big cluster, like hundreds of nodes, and see how it performs like in reality, but I don't have good numbers to share right now. I hope that answers the question. So the delta gossip is nice because it only sends the actual changed state. So instead of sending the entire thing, we send, for example, node 2 has 5 now. And this saves us a bit of traffic. What supports delta CRDTs? Currently, basically almost all of them, except registers. For them, it doesn't make that much sense, because a flag is like a boolean, so yeah, not much to save there. So, we finally loop back to the streaming dunes, and there's the oracle as well, so it's like hidden in the dunes, and you have to go there for a while, searching for some kind of stream. So, streams is the probably most overloaded word in the history of computer science. I think, maybe it isn't. Maybe addition would be worse. So, this is the number of other projects that I found on Apache Spark that use the word stream in the name, or at least call themselves any kind of streaming thingy. And that's an incomplete list, obviously, because I think each month there's like 5 new streaming things. And the problem is, each of those has their own definition what streaming is, and people would like to compare them, right? Like, should I use, I don't know, Gear Pump or Akka Streams or Beam or Scala Stream, right? You guys know Scala Stream? You guys know that it memoizes, so you're gonna get a lot of memory out of memory errors if you use it improperly. Remember that. Check the documentation. Because I actually had people who were like, yeah, I don't want to use Akka Stream, I'll use Scala Stream, which is completely different, and then it blows up. So, what is a stream in the sense we talk about in Akka Streams and Reactive Streams? It's for potentially infinite data sets. It's element by element, so it's not chunks of bytes like TCP talks about streaming, but it's element by element. So, dog, 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 cat, dog, dog, for example. And it's geared towards asynchronous processing as everything in Akka. So I will actually, that's the slides I wanted to delete actually. So if you forgive me, I'll jump ahead. If you want to refer to these slides, that's comparing like which of the streaming things does what kind of streaming, like Kafka Spark and Java Stream, which is obviously more like collections and not streams. But Reactive Streams. So Reactive Streams is more of an SPI, which when we were developing that together with other people on that group, we really wanted to have SPI in the package name. But somehow it didn't stick. Maybe it's not as of a popular acronym to use. But what it means is it's basically for people implementing APIs on top of it. Let me try to explain. So the Reactive Streams interfaces, after a year of work or so, maybe longer, like 1.5, of us, some Spring people, some Red Hat people, obviously involvement of Doug Lee from Oracle. It eventually landed in the OpenJDK under JEP 266. So once JDK 9 is finally out, this will be in the JDK. So what will actually be in the JDK? It's a thing to solve flow control, right? So if you have a slower subscriber, faster publisher, and again, a naming thing, we didn't want to call them publisher subscriber because that kind of invokes the image of PubSub. It's not really PubSub, it's point to point. But these names were overvoted. And the entire spec is about what to do to not allow this situation of buffer overflow to happen. One of the solutions is to drop all things on the floor, but when I say that, people panic. So it's a valid solution. I mean, lots of protocols do that and require redelivery, but somehow in user land, in like application development, it's not a very welcome solution. So what can we do? In one slide, basically there's a permit system, so the downstream signals looking at its buffer, okay, I can receive 3 things, so I will tell my upstream I can receive 3 things, and the upstream is not allowed to send more elements than it was given permit for. Pretty simple. And what is in the JDK is actually only the interfaces. So only that. No implementation. Like one single implementation, but it's more like an example. Okay? So why the hell do we want only interfaces in the JDK that are not even implemented? So the entire idea is interop. If something's in the JDK, you can assume that everybody will be implementing that specific thing. Would it have to be in the JDK? Debatable, but for bigger organizations or bigger projects, that's kind of a guarantee that, okay, this API will not go away. We can bet on it. So it's not that easy to actually implement this correctly. So you looked at the interfaces, it looks very simple, like four interfaces, 7 methods in total, trivial. And here's the rules of the spec. You don't need to read them, obviously. But the general point I'm trying to get across, it's actually very tricky to implement it properly. We did a lot of mistakes, other people did a lot of mistakes, and we have a properly working solution that you can just use, and that's Akka Streams. So if anyone's confused about what is Reactive Streams, what is Akka Streams, Reactive Streams is the spec, and many people can implement it, like RX can implement it or anyone else, and we implement it as well, which gives us the interop. Because for the back pressure to work, everybody needs to implement the same protocol, which this interop interface guarantees to us. Here's Akka Streams, the most boring example on the planet, and the most useless probably, but that's how people nowadays talk about, oh my god, reactive programming. It's like, so there you have it. Type-wise, it's basically sources, sinks, and flows. They align. They can be connected if the ports match, right? So a flow is something that has an input, has an output, etc., etc. So now, what have we built with Akka Streams? Obviously, you know that already. We built Akka HTTP, but that's in the past. And it's also the answer to the slides I skipped, right? You can think to yourself, okay, can I build an HTTP server using Spark streaming? No, doesn't make any sense. Can I build an HTTP server using Akka Streams? Yes, absolutely, that's the use case, right? So if you're confused about all of these streaming services and streaming data processing thingies versus Akka Streams, that's a good intuition. So what's next? We build another port, which is HTTP2. So here's a simple HTTP2 API. Well, it doesn't actually change at all from a normal HTTP API in Akka Streams because it's exactly the same, because it's only a transport difference. And what we have here is we will be serving some kind of image. You probably can't see. You can actually. Okay. So we will be serving some kind of image, but here we use the slowdown operation just to make it load a bit longer. So this is the typical like demo for HTTP2, why it's helping. And this is the same page I'm about to show in HTTP2. This is on HTTP1 with HTTPS, so it's comparable because HTTP2 is kind of assumed you're going to be running an HTTPS. So we compare HTTPS to HTTP2 here. And can I zoom? I can zoom. Okay, so this is my wonderful pictures from my vacation. But yeah, you can see here there's a lot of being stored, right? Gray basically means you're waiting. And then blue actually means you're actually sending stuff. And another thing to notice is this violet thing. That's basically SSL, handshake. New connection opening, and then doing the dance, like, oh, what protocol do you speak? I speak this. And then you can actually send data once you do the dance. So what browsers do is they open a lot of connections, and obviously you know the tricks about having more domains in your web service, website, so the browser would open more connections. It's limited to like 4 or 6 or 8. And we load in around 5 seconds or so. Here I show the SSL overhead, and this is how it looks on HTTP2. The interesting bit is there's one connection, and we can multiplex all of the data onto that single connection. Does that necessarily make sense to put all of the data out at the same time? Not really. It could be, and is still area of active research, how to properly do scheduling of pushing data out in HTTP2. But basically everybody is on the same position right now with trying to figure out how to do the optimal push there. But even with that, we're way faster. So it's nicer because it's not text encoding, but it's binary encoding. We skip a lot of things we would have to do in HTTP. So even without doing anything smart, it does some gains. And the same would apply for just 2 microservices talking to each other. You can save on a lot of connection opening and maintenance. So, as I said, Akka HTTP is becoming the default backend for Play in 2.6, which is now in release candidate phase, I believe. And if it isn't yet, it's going to be like any moment now. And this is how you use it. You just include a plugin about Akka HTTP2 support, and you do have to configure the TLS things, right? Like give a certificate, because now you're running TLS. Okay, I'll wait for the pictures to be taken. Too bad it's not of me, but I can live with that. So, and people kind of assume that if we did this change of backend, that it was only for performance. It's not for performance. I mean, the goal with performance was to not be worse than the Netty4 backend, which is a tough opponent because it's really, really good. So it's also not that we don't like Netty. I think it's awesome. But what it does give us to switch the backend is if we build any kind of monitoring infrastructure, if we do any kind of optimizations in Akka HTTP, if Play has some bug or we have some bug, we can actually collaborate way more closely. And I also mentioned the things about the typed headers and typed model, right? So we can share the work we did in the model there. So if you're curious about performance and things like that, Play has like a testing tool that's continuously benchmarking Play, and you can go to Play, prune, and that's the current benchmarks. And basically we're on par with Netty4, which is, I think, really good. We'll still be using Netty for some things, but that's like details. So, and the journey to the typed woods is a long and painful one. And like this entire talk is a journey, but we need to speed up a bit. And what I want to talk about is not what Roland talked about, which is, okay, this is the API, and this is what we're exploring with the opDSL. I want to talk about where it kind of started, which was, for example, what you may know as the typed actor. If anyone uses it, please don't. Just don't. There's no good reason to do so. The reason it was introduced, again, funny history lesson, was when Jonas and Victor were building, I can't remember which version of Akka, it looked good to Java people, right? It looks like an interface, I can understand that, and maybe Akka isn't that scary, right? So it was a nice way to kind of show people, hey, we're not that scary. But it comes at a cost. It uses reflection to basically weave messages out of these methods. It encourages blocking, actually, which is the main sin you can do in Akka. And it's not really, it doesn't look like messaging. It's like we devolved to RPC. So, you know, don't use that. Then there was a brief expedition to the typed channels, which Roland, who was presenting here, was exploring a lot back then. And that was sadly, we got a way better API now, but that was removed into free already. The downside was it actually would have to use macros, was very heavy on the type level things. So even for simple stuff, you would get really nasty compile errors. Whereas with a new typed API, the simple stuff is simple. If you want to go crazy with the opDSL, you can go crazy with the opDSL. So then after years of going around and wiggling around and exploring things, we arrived at the current Akka Typed, which I need to fix the slide, I'm sorry. I keep updating. Okay, so in Akka 252, that was a funny snapshot version that we wanted for early feedback. You have two styles, mutable and immutable, and because this was explained in depth by Roland, I will not get much into it, but a very quick one. Okay, here picture time while I explain. So now it's mostly about behaviors. We always talked about behaviors, but it wasn't a type. So now it's a behavior of type T, where T is the type you can receive a message of. And sender is gone, so all of the nasty errors with handling futures inside of actors and closing over the sender accidentally, that's gone because sender is gone. And actually removing sender is a good thing to begin with, because it allows you to do a nicer design where each message kind of contains and can name the actor ref and can type the actor ref that you're going to be replying to. So, quick side story, why do we have two styles? We have untyped on the left, so that's how we call it Akka Classic. Has a good ring to it, like classical music. What? No, it's classic. So, and on the right, the mutable style. So the mutable style basically looks very similar to the old one. Why do we want that style? For one thing, it can be a bit faster. I don't think many people will actually care, but it's easy to migrate to, right? Because, and you already get the benefit, right? It can only handle commands of a certain type, right? Here, greet a command. So without a lot of rewriting to the new style, you already can get the benefits very easily. So that's one of the reasons why you have that. And the recommended style is more immutable, more functional in a way, and it basically feels and learns a lot from what we did in Akka FSM. Right? So if you liked finite state machines, that's basically it. Because at the end of each behavior, you say which other behavior it should become. Right? And actor same basically means, yeah, I'm still the same behavior. We have some docs, we have some great blog posts about it, and we're out of time, so I need to go quickly. So, Versa Java DSL. If you're a Java person, we made a DSL that looks pretty okay. It uses lambdas, so it's the best we could find. And if you want to learn this stuff, we currently do not have super comprehensive documentation. It's like basic documentation for it. However, we did a nice blog post series about all of the different features that it has. So go to the blog. Okay, we're over time, so I need to go quickly over the alpaca farm. What is alpaca? Collection of connectors and this funny animal. And if you're curious about like helping us and the community, this would be an awesome place to start, because it's pretty easy to contribute like connector to your favorite technology, and it's also a very, very inclusive and easy to get started with. It's easier to get started with Alpakka than fix crazy race conditions in Actor Dungeon, right? So I would recommend that if you have the time. Okay. And the pretty much last big feature is, which is already shipped, you can use it already, which is the new remoting. Quick note, never ever use remoting directly, use the cluster for reasons I can go in depth later if you want. Basically, cluster, of course, builds on top of remoting. So all of the features I talk about here are used by the cluster, but cluster has more smarter failure handling. It actually will do the thing you would want it to do, whereas remoting is very simple. If a connection breaks, it breaks forever, and you would have to reinvent the cluster basically to have some kind of resilience. So, what's the new generation of remoting? It's UDP based, it has active compression, manifest compression, it has dedicated lanes for big messages, which many people often do. They send like a really big message, which would lead in the old remoting to just clogging the pipe, how I refer to it. In the new one, you can have a specific lane that can have the big nasty messages without hurting the rest of the system. How difficult is it to use? You just say on, and you get a 10x improvement in performance. Pretty good. The address would change a bit, and now it's UDP and not TCP, so if you're behind firewalls, you would have to adjust that, right? But the rest, there's no API influence, everything works as if you would like it to. That's for like performance geeks. In stable state, almost allocation free, almost, because obviously if you deserialize an object, that has to become the object, right? And compression. If no one has ever looked at how a message looks in Akka, this is how a message looks. And you may wonder, okay, which part of that is the payload? So the last 5 characters. The message is hello, and the rest is who sent the message, who's the receiver of the message, and also like information about the manifest of the payload. With compression, we can get that down to like 30% of that, so pretty good. And it's also dynamic and scales automatically. New stuff, we're looking at multi-data center stuff, about which I don't have much specifics, but I do want to get your feedback. What would that mean? Because people say, I want multi-data center stuff. And then we ask, what would you do with it? I don't know. It's so cool. So if you have multiple data centers, we would like to hear your actual story, okay? It could be like, we have this wallet thing, and the wallet can fail, so we have to go to India, to the other data center, to, an actual story, not a story like, because I have multiple data centers. That's not a story. And 5 million things I couldn't fit on the map or in the time. So new docs engine with Scala fiddle support, so you can execute Akka code in the browser inside of your documentation. Now it's markdown, so you don't have to attempt understanding restructured text, which no one ever did, including us. We have a Lightband kickstart, so you can go to a web page, develop a Lightband, you click 5 times, I want a cluster project, you get a cluster project in a zip file. We have monitoring coming on, so we monitor distributed the cluster sharding, where the shards are being allocated, we monitor HTTP, we even have tracing, so we can actually, you get a request, right, and then it's being routed through Akka HTTP to some route, and then you send it to an actor, we can actually track which HTTP route it hit, and inside the actor we can tell you where this request came from, and what the latency was, etc., etc. How difficult is it to use? You basically say on. There's a pattern. So distributed tracing works a bit. It's going to be way better, like with the thing with the routes I just said. That is a commercial thing. So yeah, we gotta eat somehow. There's also ops clarity if you have multiple systems. So last things. I know I'm the only thing like between you and a lot of beer, so I respect you not leaving the room. Thank you very much. IntelliJ guys. Last, like literal. Go to the IntelliJ booth. They have started working on Akka features, which basically whenever we find something that we think they could maybe do like a feature, we open them a ticket. I urge you to do the same, because when they see there's a community that wants features, then for one thing, they see there's like demand, and then your favorite feature you always wanted could be implemented. So that's a really cool thing to do. There's Akka.net and Akka.js. We're obviously part of the Scala index. And summing up, I think that's like only the beginning, and there's way more cool stuff coming very soon. And special thank you to all the contributors, which we recently started just giving out committing rights and actual ownership to many of the other projects. Some of them are here, so that's my thanks to them. And if you try to remember some of the names, and if you see the guy, just grab him and give him a hug. No women so far in this group, but maybe soon. So, we love contributors, that's my free ebook. And if you have questions, I propose to do those over beer. It's easier to talk over beer, I think, like especially for nerds. So thank you very much, and thanks.